Why does the wheelbarrow make a heavy load feel easier to lift? You are not destroying the weight of the load. Instead, the wheelbarrow changes how the force and distance are arranged. This video introduces simple machines and mechanical advantage. A simple machine can reduce the input force we need to apply, but it usually requires us to apply that force over a larger distance. The key idea is that machines do not create energy. They help us trade force for distance. In this lesson, we will look at levers, pulleys, and a wheelbarrow example to see how that trade-off works. Let us begin with what simple machines do and what they cannot do. Simple machines are devices that can multiply or increase the effect of an applied force. Common examples include levers, gears, pulleys, wedges, and screws. The important point is that a machine can make a task easier by reducing the force we need to apply. But that advantage usually comes at the expense of distance. We may apply a smaller force, but we apply it through a larger distance. Energy is still conserved. A machine cannot do more work than the energy put into it. In an ideal machine with no friction, the input work equals the output work. In a real machine, some energy is lost to friction, sound, or heat. So a simple machine does not give us free energy. It changes the way force is applied so the task becomes more manageable. Mechanical advantage tells us how much a machine multiplies the force we apply. Mechanical advantage is the output force divided by the input force. The output force is the force the machine applies to the load. The input force is the force we apply to the machine. If the mechanical advantage is greater than 1, the output force is larger than the input force. That means the machine helps us lift, push, or move something with less applied force. If the mechanical advantage is equal to 1, the machine does not multiply the force. It may still be useful by changing the direction of the force. If the mechanical advantage is less than 1, the output force is smaller than the input force, but the machine may increase speed or distance instead. Now let us look at a few examples of machines with different mechanical advantages. This slide shows 3 different machines. A crank is a type of lever that rotates around a pivot. Cranks are often designed to have a large mechanical advantage because the handle is far from the pivot, giving a large lever arm. The automobile axle and wheel example shows a case where the mechanical advantage can be less than 1. The wheel has a much larger diameter than the axle, so the system may trade force for motion in a different way. The ordinary fixed pulley changes the direction of the applied force. If you pull down on the rope, the load moves up. But a single fixed pulley does not multiply the force. The tension in the rope is the same throughout, so the mechanical advantage is 1. That means a fixed pulley can make the task more convenient without reducing the required force. Pulley systems can multiply force when more than one rope segment supports the load. In an ideal frictionless pulley system, each supporting rope segment has approximately the same tension. If 2 rope segments support the load, the upward force on the load is about 2 times the rope tension, so the mechanical advantage is about 2. If 3 rope segments effectively support the load, the mechanical advantage is about 3. If 4 rope segments support the load, the mechanical advantage is about 4. The trade-off is distance. If a pulley system lets you lift a load with 1/4 of the force, you usually need to pull about 4 times as much rope to raise the load the same height. This is another example of the force distance trade off. The machine reduces the required input force, but energy conservation still limits what it can do. Now let us apply the same torque and mechanical advantage ideas to a wheelbarrow. In this example, a wheelbarrow supports a load. The load has a perpendicular lever arm of 7.5 centimeters, while the hands have a perpendicular lever arm of 1.02 meters. The combined mass of the wheelbarrow and load is 45 kilograms. Part A asks what upward force you must exert at the handle to support the wheelbarrow and its load. Part B asks what force the wheelbarrow exerts on the ground. The wheel acts as the pivot point. The weight of the load acts downward with a short lever arm. Your upward force at the handles acts with a much longer lever arm. Because your lever arm is long, you do not need to apply a force as large as the weight of the load. Before calculating, let us predict the answer. The total weight is about 441 newtons. But because the hand lever arm is much longer than the load lever arm, the required hand force should be much smaller than 441 newtons. Now let us use torque equilibrium to find the hand force and force equilibrium to find the ground force. Let's first write down the given values. The output lever arm LO is equals to 7.5 centimeters. So this is 0.075 meters. And the input lever arm Li is 1.02 meters. And the combined mass is 45 kilograms. For part A, we use torque equilibrium about the wheel. The clockwise torque from the load must balance the counterclockwise torque from your upward hand force. The load torque is the weight of the wheelbarrow and load multiplied by the short lever arm. We can write down the net torque is equals to output force multiplied with output lever arm, and that is in the counterclockwise direction, so that's positive, minus input force times the input lever arm, and that is in the clockwise direction, so that's why it is negative. And this is equals to 0 because of the torque equilibrium. Now we can rearrange this equation, so we can send this part to the right hand side of the equation, and we get output force times output lever arm equals input force times input lever arm. So to find input force, we can rearrange this equation, which is output force times output lever arm divided by the input lever arm. And now we can substitute the values. Output force is mg, so 45 kilograms multiplied with 9.8 meters per second square multiplied with output lever arm 0.075 meters, and we divide this by the input lever arm 1.02 meters, and we get 32.4 newtons. So you need to lift upward with only 32.4 newtons at the handles. That is much smaller than the total weight because the input lever arm is much smaller than the load lever arm. For part B, we use vertical force equilibrium. The wheelbarrow is not accelerating vertically, so the upward hand force plus the upward normal force from the ground must balance the downward weight. So we can write net force in y direction equals to input force plus the normal force minus the weight, and this is equals to 0. So we can rearrange this to find the normal force. So the normal force is equals the weight minus the input force, and we can substitute the values. weight is 45 kilograms multiplied with 9.8 meters per second squared minus the input force is 32.4 newtons. And we get 409 newtons. This 409 newtons is the force the ground exerts upward on the wheelbarrow. By Newton's third law, the wheelbarrow exerts an equal magnitude force downward on the ground. So the force the wheelbarrow exerts on the ground is 409 newtons downward. The main takeaway is that the wheelbarrow provides mechanical advantage by giving your hands a long lever arm. You apply a smaller force but over a larger distance.